start dimming the lights. Cool. Give folks a second more to sit down. Alrighty, I'm going to start. Hi everyone, I'm Brad Nelson. I work at Google, and I'm here to talk to you today about native code in the browser and all the things that it should be able to do for you in the not too distant future. If you do want to follow along with the slides, they're up online at gonacl.com/magic. Okay, so if you get nothing else out of this talk, what I hope you'll come away with is an increased set of expectations about what the web platform should be able to do for you as a developer. The reason for this is very basic. It's good platforms are platforms where people are doing innovative things, and platforms that get in the way of people doing innovative things are not good platforms. And as a browser developer, I care very much about making sure that the web platform is a place where people can do things that are on the cutting edge. And if you're finding that the web platform is in your way, make noise about it. Browser developers really do want to hear about the problems you're having and the things that you can't do. So let's talk about the virtues of the web. So the web is a good thing, and one of the key reasons is that it's an open place. There's no one government or company that owns the web. There are multiple vendors for everything, for browsers, for the servers, for all of the infrastructure that brings the web to you, the payment processing, all that stuff. It's portable. When users go to a website, they have the expectation that the website sort of means the same thing, whether they go to it on a phone or on a tablet or on a desktop, and regardless of operating system. It's secure. You trust it with your bank account. What's kind of unique, I think, about the web is that even fairly naive users have a pretty good model of actually what's going on in terms of security in the web. And I think this relates to the fact that the web has another property, namely that it's ephemeral. When you go to a page and then you go away from that page, there's very little of you that sort of stays behind. There are things that can stay behind, but I think users have a kind of a mental model of the sorts of things that they can expect that they're leaving behind and the things that are still running when they leave a page. But I'm going to go out on a limb here and suggest that I think there's actually something missing from the web. And the reason that I think this is that too often when I see people doing clever and innovative things, I notice that they're doing it in other ways. They're going directly to native APIs on the devices they want to target. They're targeting mobile directly with on iOS and Android. And I think it's because the web is actually missing a virtue that it really should have. I'm going to say that it's not powerful enough. And that might be controversial, but and I think my belief is that the reason that it's not powerful enough is that in general it is still not good enough at giving us something I call native code. As we're a few days short of Halloween, and as I have my trusty magic wand, I'm going to make a further leap, and I'm going to suggest the metaphor that what's missing from the web is the magic of native code. So, okay. So what I'm going to do is talk you through the reasons that I think native code is something that you should care about and why it's great, and what you can do with it. I'm going to talk about why the other options that are available to you don't work that well. I'm going to talk a little bit about security because security and native code have had a kind of a fraught relationship over time. And then I'm going to talk about some emerging standards, some cool stuff that's going on with the various standards groups. And I'm going to talk about what you can start using right now. So there are some magic words that I'm going to use in the course of this talk, and I'm going to define them now because I'll probably use them without thinking. There's a technology for native code called Native Client, which is often abbreviated NACL, and I'll probably unconsciously call it that. And it has there's a related technology called Portable Native Client. There's something called Emscripten, which is a tool that converts from C and C++ code to JavaScript. And there's a related technology called ASM.js, which is a way to represent machine-level code contained inside of JavaScript. So native code, what do I mean by native code? Well, on a really basic level, I mean code that runs really fast, fast enough that you're kind of down to the metal. And I think getting down to the metal is actually kind of the critical attribute here. You've got very powerful computers nowadays. You've got very powerful computing devices of all sorts. And if you want to have direct access to them to do sort of the most that they can possibly do, you need to be down to the metal. Now, even if you don't actually care about raw speed, there's another reason you should care. Because speed is also efficiency, and efficiency is power. And so if you're trying not to burn up the phone in my pocket, then you also care about efficiency. Another thing I think that's important is actually access to what I'll call native APIs. And by this I mean access to sort of all of the other things on the hardware that you might want to reach out and touch. The GPU, the ports, the networking stack, the sound system, all of these things. And there's a related thing that might not be immediately obvious with native code, which is it's actually kind of related to the possibility of breaking the monopoly that JavaScript has on the web platform as its only language for development. Because native code is a gateway to other languages being something that you can use on the web. Another important thing is threads and shared memory. We have lots of cores in our contemporary systems, and they're only going to have more cores. And I think something else that's important is dynamic code generation, the ability to not only have native code, but be able to generate it on the fly. So let me talk briefly about something I've been involved with for a while. At Google, we've been trying to get native code on the web for actually a very long time, going almost back to 2008. Native client is a technology that lets you run machine code in the browser safely. And you're saying machine code safely. Wait, that doesn't sound right. I'll talk a little bit more in a moment about why that's a reasonable claim to make. There's also a portable variant of it, Pinnacle, that I mentioned before. And native client is very fast. It's 80 to 95% of the speed of raw native code. It has SIMD support. It supports threads and shared memory. It has supports for shared libraries, and it has just-in-time compilation support. It's mature and powerful, but it is Chrome only. And as I mentioned, I'm going to talk about some ongoing standards work. And the way I want you to think about native client is think of it as the thing that you can do now that's a preview of what you're going to be able to do in a few years on all the other browsers. Then there's something called Emscripten, and this related thing called ASM.js. The idea here is that you take your C and C++ code and you compile it to JavaScript, and you represent the memory space of your C program as an array buffer. And this gives you actually one nice thing that native client does not. It gives you synchronous access to JavaScript in the DOM. It's faster in some browsers than others, and there's kind of ongoing change in this space that you're likely to see. This is because you're going through JavaScript as an intermediary. I'll talk a little bit more about the details of that in a moment. It has a high percentage of raw native speed. It's definitely more portable than native client, but it's missing a number of things. However, there's a bunch of cool standards work that's going on that is actually working to correct that in the very near future, something that I'm very excited about. Both of these technologies for native code have a bunch of APIs that they give you access to: 2D graphics, 3D graphics, sound, media streams. They each have a type of local storage that they can do. And in some contexts, you can even get network access with native client apps if they're in the Chrome Web Store, and clipboard access. So let's talk about some things that native code can do. So the obvious thing is that if you have computationally expensive code and you want to run it in the browser, then you definitely want native code because you want to get all the cores and be able to do sort of all the things. And native code is really good for that. It means that there's hopefully not too much you have to change from the high-performance code you started out with. You might have to make your code a little bit more portable than it was previously, cope with some unusual constraints, but that's definitely one use. And the consequence of this, of course, is that game developers, of course, are always desirous of having native code in the browser because this lets them take their application that they're running in other contexts and bring it to the web, bring it to the various web stores that are out there. And so that's an exciting thing. And there's all sorts of game applications that folks have ported over the years to native client and Emscripten. But it's not just games. If you've got any large C++ code base, or actually code bases in a range of languages, you're not going to rewrite that in JavaScript. And so, for example, the Quick Office folks have taken a document editing and spreadsheet editing suite and brought that to the web using a native client. In general, if you're trying to do any amount of heavy computation, if you're trying to do photo editing or video editing in the browser, and you don't want to have to round trip that to the server, then you're going to want to do that locally on the machine using native code. GIMP in the browser. If you've got a custom codec that you want to use, currently you've got a rather unfortunate situation that you're in. If you've got some clever idea about how to compress things, you have to potentially wait until you can disseminate that to all the browsers before that's something you can actually use. Whereas native code opens up the possibility that you can devise your own codec and use it right away. Similarly, if you're trying to do something cutting edge, if you're trying to do speech recognition in the browser, you may not want to wait for that to be a built-in facility. You might want to be able to use what you have there, namely access to sound and computation, and do it yourself using the range of libraries that are out there. If you want to chew through a lot of data, there are times when you don't actually want to send everything up to the cloud. For example, Google Play Music offers the option to let you upload your CD collection to the cloud. Well, it doesn't actually upload all the CDs. That's a lot of data to push up. So what it does is a local scan of your CDs, and it generates a fingerprint and then sends the fingerprint up to the cloud to verify that you've actually got the right CD. And it's doing this work using native client. If you've got some complicated protocol that you want to make sure is secure, you don't want to re-implement that from scratch and then vet that you did everything exactly right in JavaScript. You want to take the code as is and deploy it using your existing code. Another application of this technology that I'm kind of personally excited about is the idea of being able to do development in the browser and not have to round trip to the server. And so we've even been able to take things like compilers and interpreters and run them actually in your local client, again, using native client. Another cool application you may be unaware of, there's something called the application runtime for Chrome, which lets you take an Android APK and convert it to run on Chrome OS devices. It's actually capable of converting it to run on any browser, but there's some restrictions about where we allow it to run. And you can what it's doing is it takes the entire Android operating system, it's built into native client, and then your application is running sandboxed with a mini copy of Android deployed to the Chrome Web Store. And a number of folks have used that to bring applications to the Chrome Web Store and Chromebooks. But you're thinking to yourself, well, I'm a JavaScript developer. What does this have to do with me? So one thing that is relevant to you is that there's a lot of code out there in C and C++ for doing interesting things. And you may not need to have your whole application be in C++. It may be something where you want to use one library. You have some compression that you want to do that's novel, or you have some encryption that you want to do. As I mentioned before, maybe you have a codec that you would like to incorporate into your application. Or another possibility is that somebody might devise a widget that you could reuse that does something that's more powerful than what you can currently represent with JavaScript in the DOM. But that raises another point. Folks often ask me, well, aren't JavaScript and the DOM enough? They can do quite a lot of things, and I mean, there are a lot of things you can do with JavaScript and the DOM. But unfortunately, we've had a good ride for the last 7 to 8 years, but to a large extent, JavaScript performance is plateauing. What's happened is that we started 7 to 8 years ago with browsers that had sort of really bad interpreters, and we've gone to very finely tuned just-in-time compilers that are very carefully written. But the big wins are mostly gone. And the other problem is that the DOM is inherently slow and has this kind of a weird singly threaded relationship with JavaScript. And so the two are sort of ping-ponging back and forth in a single thread on a single core. And in a world where the gains that we're going to see in the future with computing devices are more cores, this is not a good situation to be in. The problem in both cases is that the browser is being asked to do something kind of magical. It's being asked to infer what you as a developer meant and sort of backward guess what you had in your head. So for instance, with JavaScript, there's no types out of the box. And so it's being asked to reason about what kind of types you actually meant, what you were thinking about in your head, and then make guesses in some cases. And if those guesses are wrong, it has to fall back and do a lot of work to compensate for that. And the same thing happens with the DOM. People go to great lengths to sort of, they have some model of what they would like to display, and then they have to represent it in the DOM, and then the browser has to decode what they actually meant. So the other issue is that JavaScript performance is inconsistent. It's great to be optimized, but optimization doesn't kick in right away. Instead, what happens is that you run at one speed, things get optimized, then you run at another speed, and just when you think you've got stable performance, then the garbage collector kicks in a little bit, and you've got a temporary bubble in your performance. And what's worse, remember I said that JavaScript makes guesses about what you meant with types, and if it guesses wrong, it has to de-optimize, and you get kicked back down to that lower level of performance. So one of the virtues of native code is that it runs at an even keel. It has consistent performance. So if you're trying to hit 60 frames per second, you can do that consistently frame after frame after frame. Another issue with JavaScript is the way that it uses memory is kind of pathological in terms of what works well on contemporary systems. JavaScript accumulates lots of garbage and then compacts it on a regular basis. And in comparison, native code does sort of what your computer actually wants it to do, which is it runs through data in typed order, in cache coherent orders, in sort of uniform patterns. And so that's another aspect of performance. So I kind of lied to you a moment ago, and I said that JavaScript can't convey type information, and I'm going to use this as a moment to give you a sort of a little mini description of how ASM.js works. So as we all know in JavaScript, the numbers are all float 64s, right? But if you kind of dance on one foot, you can actually tell modern JavaScript engines that you actually mean some other data type. If you call a function called fround, you can round your floating point numbers to a 32-bit floating point number. And if you do this incessantly at every time you do an operation, contemporary JavaScript engines will pick up and say, oh, he means that this is a float 32. I can represent this as a float 32. And similarly, if you OR with 0, they will pick up and say, oh, yeah, he means this is an int 32. Or if you, who knows what triple right shift does. It's an unsigned right shift. This can be a hint to JavaScript that you mean an unsigned int. And similarly, if you use array buffer and typed array, you can actually convey quite a lot of information about what kinds of data types you mean. And you can actually represent a large part of the abstraction benefit of pointers and their typedness by using a typed array. And all of these things put together, wrapped inside a closure, is approximately what ASM.js is relying on to get decent performance in browsers that don't specifically optimize for it. Add to that there's this little use ASM sentinel at the top of it, which is a hint that if you have special optimizations that apply to code that have the property that every type telegraphs its type information, then you can even have higher performance implementations. And this allows you to represent fairly low-level stuff in JavaScript. And so you can have things like Sterling, where you're walking down an array with a pointer, and as you can see, you're incessantly ORing with 0 to say, oh no, this pointer is an int, and when you access the heap, you're doing it through that typed array. And that lets you convey type information, which lets you recover a pretty large chunk of the benefits of native performance. But now I'm also going to make another sharp right turn and talk about security, because I mentioned native client before and secure machine code, and you're thinking to yourself, yeah, he's nuts. So the real question with security is are you a good witch, or so if you're a good witch, you want the good stuff, right? You came for the high performance, the games, the video processing, the compression, the encryption, or you came for compatibility. You wanted to run some language other than JavaScript, and you wanted language freedom. But, or maybe you came for more APIs, or more direct APIs. But you could be a bad witch. And you're a malware author, and you came to steal my data and to stick around when I leave the page and pretend to be something else, and to eavesdrop on me. Or even if you don't have completely bad intentions, maybe you have partially bad intentions. And so maybe you don't care about the portability of the web. Maybe you're going to write your code only to work on one architecture or on one operating system, or only on one browser, or only in one configuration. And so the key decision that is needed for security is to recognize how to separate the good and the bad. Historically, this was the technique that was attempted by a variety of folks, and this is the ActiveX dialog. And as you all may know, there's really no good answer to this question. If you answer yes, then you're completely at the mercy of whoever provided this. And if you answer no, well, then you don't get to use the application. So there's a big graveyard of past attempts to offer something that resembles native code in the browser. ActiveX, which, for example, in Edge, Microsoft has been moving away from. There's something called NPAPI, which is a plugin technology that's available in a number of other browsers. And it has many of the same drawbacks. And for that reason, all the browser vendors are starting to move away from it. Google Chrome actually now no longer allows NPAPI plugins. And Firefox has just announced that they too are going to drop NPAPI support. Something that has the flavor of native code was Java. It was something that evolved in the early days of the net. And what happened there was that early implementations were simply not hardened enough against pathological inputs. And it also suffered from a mismatch in the API surface that it offered. It offered too many things. And then as we sort of locked down what you could do with Java, it was difficult to deploy this to browsers. And so what happened is that browser vendors and administrators and whatnot started turning off Java because they just couldn't be confident in its safety. Flash has a similar flavor. Flash was actually, very, very successful at offering a slightly different API surface than the web in general, and people used it for that reason. It does give you access in some context to shared memory, or also some access to other low-level things, direct access to sound buffers, which is one of the reasons people would use it. But unfortunately, because there's that mismatch between the expectations about what the security surface of the web is versus what Flash offers, Flash too is sort of in decline. And this sort of highlights the challenge that if you want to offer APIs, they kind of need to be a match for what the web expects. So how does native code, so what do you need to make native code secure? So you want an API surface that I think is equivalent to JavaScript so that people can reason about it. You want to have hardened APIs, and in particular, why hardening is especially important with native code is that native code gives you sort of new opportunities to really hammer at an API that you might not have had with JavaScript, or you might not have had quite as much direct control. But the main thing is you need a secure container. So for a native client, the way this works is we have not one, but two sandboxes. We have an outer process sandbox, and we have an inner static verification sandbox, which I believe is the more important of the two. The outer sandbox is the same sandbox you're familiar with from Chrome in general. It's the same sandbox that keeps your tabs isolated from each other and from the operating system. Native client is off on yet another process that's isolated even further. It talks through the renderer to the browser, and so it has that level of OS protection. But inside of that, it has something called software fault isolation. And this is the basic idea here is that you verify that things are safe before you run them. And now how can you do that with machine code? Well, you disassemble everything. And you make sure that you limit the set of instructions that are allowed to ones that you can reason about so that you can make good security decisions. You then have to be able to reason about them enough that you can say that all of the possible control flow through the code is safe. And then you also need to be able to assert that all of the data accesses are safe. And this is what NACL does. Whenever you load something, it is validated before it runs, and that way you can be confident, in addition to that outer sandbox, that it's safe. You also have to restrict the I/O interface, make sure that you can only talk to the outside world through a limited surface. And so NACL keeps code and data separate, and so that's a big part of why it's safe for you. So now I'm going to gaze into the future a little bit. Tomorrow, and tomorrow creeps in this petty pace from day to day to the last syllable of recorded time. So I'm going to look into my crystal ball, and I'm going to see something from the near future. I'm going to tell you about something called SIMD.js. So SIMD.js is a technology that gives you access to SIMD in the browser. SIMD is a single instruction, multiple data. The idea is that if you're trying to manipulate something like a vector of 4 numbers, you want to be able to maybe do this with a single machine code instruction. You're probably familiar with the names of the instruction set variants on the different systems, SSE, AVX, Neon. And the idea with SIMD.js is this is a standards effort that we've been working on with a number of different browser vendors to bring SIMD to the web. We've been focusing in the short term on only the 128-bit types, mainly because these are available on all of the different architectures, and just it's an easy point of agreement. They all work more or less the same. What this amounts to is that these are instructions that let you manipulate 4 floating point values at a time, or various slices, integer slices of 128-bit value. This is great if you're doing, the floats are great if you're doing graphics operations. You often have vectors of 4, and the integer operations are especially useful for pixel manipulation. You can load and store these to array buffers so that you have a way to get them in and out. And the really key thing is that there's a very close correspondence between the SIMD.js functions and the SIMD.js instructions. And so typically if you have SIMD.js code, you can be reasonably confident that each SIMD.js function invocation will loosely correspond to a single SIMD machine code instruction. So you can try to write very efficient code. And what's really exciting about this is at stage 3 at TC39. For those of you unfamiliar, TC39 is the standards body that oversees JavaScript. And there are 4 stages for a standard to go through the pipeline at TC39, and they've recently done a marvelous job at optimizing their process so that things actually can get through a lot faster. So you'll hopefully see a lot of things get through in the near future. So there are 4 stages, as I mentioned. So stage 3 is 1 stage away from 4, which is it's now a standard. What stage 3 means is that the JavaScript standards body no longer has any JavaScript-specific objections to the standard, and that the only changes that will occur to the standard are based on feedback from browser developers and from users. And the browser developers are all in the process of readying versions, prototypes of this that they have in their browsers to release. And at stage 3, they're free to just release this stuff into the wild for folks to try it out. And so I expect in the coming months that this will go out there, and I look to you guys to give us that feedback and make sure that this does useful things for you. Now, you're wondering, of course, how do I use this? And the biggest place where this comes in is actually in the context of ASM.js, because one of the key uses for SIMD.js is that this is a way for ASM.js to offer you access to SIMD operations. But you can use SIMD.js directly. What it will add to JavaScript is a new global object, the SIMD object, that you can that has a bunch of operations for various different types of arithmetic operations hanging off of it. And there's some additional types that get passed around as well. So it is something that you can code by hand as well. In the near term, at least some browsers may only offer the most extreme optimizations for SIMD.js in the context of ASM.js, but in the fullness of time, it's likely to be something that you could imagine programming directly in JavaScript. So I'm going to look again into my crystal ball and talk about something called shared array buffers. So shared array buffers are basically a way to provide shared memory for JavaScript. And the reason that, so the way they work, so currently you have array buffers, and array buffers are a way of representing type memory to JavaScript. And you have web workers, so you have multiple threads in JavaScript. But currently, when you send an array buffer to a web worker, you have one of 2 options. You can either send a copy, and then you'll incur the cost of copying that entire array buffer, or you can do something called array buffer transfer, where the sender loses access to that array buffer and then hands it off to the worker. And the copy that's retained there is it's neutered, is the terminology that's used. So the trouble is it can't be in 2 places at once. You're either paying the cost of a copy or not. And the idea with a shared array buffer is that you'll be able to hand it off to a worker and still hold on to a copy of it yourself. And so both the worker and the parent can touch it, and then you can hand it off to another worker. And so everybody can share access to that memory. And added to that are some synchronization primitives. They're very low-level primitives, just atomics and futexes, but the assumption is that there'll be libraries that will be built up on top of these. These are sort of the most simplistic primitives that we could build shared memory on, but you'll have higher-level libraries to provide you mutexes and condition variables and things like that. So this is at TC39, this is at stage 1, which is a little bit potentially deceptive. So the stages, there's actually a stage 0, by the way, which means you've sent them an email and you have a pulse. But stage 1 means that the committee is actually interested in pursuing this general area of functionality for JavaScript. But the interesting thing with shared array buffers is that both Firefox and Chrome have an implementation already in place behind a flag, or actually in the case of Firefox, it's in Firefox nightly. And so while this is fairly early in the TC39 process, there are reasons to hope that this will be something that will gracefully sail through the process. But there are some issues. Now, I should mention, by the way, if you're wondering what do I want shared memory for, the real thing that this provides is threads. And you're thinking to yourself, well, wait, JavaScript has threads, right? Web workers. The key problem is that post message is actually very slow. It's far slower than you might have otherwise assumed. A colleague of mine actually did some extensive measurements of it, and to give you a sense, it actually can take on the order of a millisecond to 10 milliseconds to post message to a worker, especially in terms of latency. You know, 1 to 10 milliseconds, that's down in the realm where you can hear it, where you can feel it vibrating. So it's way too slow for high-speed communication. And so a big part of why you might want shared memory is fast synchronization. The other, and the underlying goal, of course, is to be able to use all of the cores. And the reason this is important is that the same colleague that was doing testing with us has discovered that because of the high latency of communicating using post message, if you have a job and you say split it into 4 and distribute it across multiple jobs, if you have to do anything other than the most trivial level of communication to coordinate between those workers, you can eat away all your performance. You think you're doing 4 times as much work, and you end up getting nothing out of it. So it's actually very critical to have fast synchronization. There's a side effect of this, which is it opens up the possibility that you'll block on a background thread, which is potentially a new piece of territory for JavaScript to go to. But the key thing is that this opens up the possibility of different concurrency models. Up until now, everything in JavaScript has been asynchronous programming. And the reason this is important is that C++ code, of course, very often expects threads. But there's another reason that's actually almost more important than threads. A lot of C and C++ code, if you're not going to modify it, has the assumption that you can block in various contexts. And without the ability to block, it can be very tedious to port applications, because you'll often have to sort of unravel them to express them in a form that you can sort of pump from JavaScript. And so being able to express the blocking and then move C++ code off to a worker and then have it block there while the main thread marshals things can be very effective. So there's some challenges that the committee working on this is going to have to confront. Well, one of them is just that concurrency is hard, but the real issue is that to a certain extent the JavaScript community is under, I believe, the mistaken impression that they've solved the problem of concurrency, and that the answer is asynchronous programming. The trouble is that this is a little bit of a false belief system. The thing is, you know, folks will think, oh, I do asynchronous programming, I don't have the problems that folks doing shared memory have, but you actually have a lot of them, you just know them by different names. So, for example, you may think you don't have deadlock, but it's just that you know it by a different name. When you drop an event on the floor, or you have a promise chain that doesn't hook up to the right place, that's deadlock. Or if you have handlers that can't handle events in all orders, that's a data race. And so it's the same kind of problem, it's just you're experiencing it in a different way, and you perceive it differently. Another issue that actually spent a lot of time was spent on at the last standards meeting was concern about side channel attacks. This one I don't actually suspect is going to derail this effort, but it's kind of, there's a humorous irony, because a side channel attack, by the way, is the idea that if you have 2 programs running on the same machine, if you're very careful about measuring how long something takes in the one, you can potentially eavesdrop on the other. And up until now, this hasn't been much of a concern for the browser and for JavaScript, because in general, they're not fast enough to be able to observe things at a fine-grained level to be able to observe what's going on elsewhere. In general, I think most of these attacks are overblown, and in most cases, the right mitigation is a change to the operating system or a change to the kind of code that you're running to make it immune to these. But this is something that is definitely going to be have some thought before shared array buffers get through the committee. There's a little bit of puzzlement about what will happen in the main thread, because a sacrosanct rule in JavaScript is that you don't block the main thread for anything. You always kind of return back to the event loop. But what if you actually want to wait on a concurrency primitive to communicate with a worker? but not through the event loop. And there are reasons that you might want to do that if you want to have fast synchronization, especially if the main thread is the only one that can talk to certain APIs. And so there's an open question about to what extent and in what way we allow blocking on the main thread. There's also the question of which web APIs that currently can interact with array buffers will also interact with shared array buffers, and how that will work. You know, if the data can sort of change from the time that you made the call to when the call is actually acted upon, there can be security concerns. And I think a broader concern is just that this could have a big impact, even if you have no interest in native code at all. One side effect of having shared array buffers is it opens the possibility of blocking concurrency in JavaScript, and it means that somebody out there, somebody is going to write that framework that lets you write synchronous code in JavaScript using shared array buffers as a building block. And so it opens a sort of a Pandora's box of possibilities in terms of how it interacts with the rest of the web platform. So let me gander into my crystal ball one last time to talk about something called WebAssembly. So this is a particularly exciting effort. This is, we're actually, all of the browser vendors, after having now had a variety of experiences with native code, we're actually sitting down together and we're talking and meeting regularly and discussing all the fun things that we can do with native code. And there are pros and cons to a lot of the approaches we've taken. You know, ASM.js has been this kind of incremental evolutionary approach, but it suffers from a very verbose encoding that's kind of baroque and roundabout. You're kind of cutting a channel around JavaScript, and yet JavaScript is still there. You still have to parse code. And so we're talking about coming up with a cross-browser binary standard that lets you take native code and run it in all the browsers. And we have a WC3 working group, and we're working through a lot of experimentation and prototypes in an ongoing way. And I have a lot of confidence that this effort is actually going to result in something so that in a few years, a lot of that functionality that you see in native client will be something that you'll have in all the browsers. The thing that we're working towards currently is we're calling it a minimum viable product. And really what this means is that we're working towards offering a version of WebAssembly that has approximately the same feature set as ASM.js. There are a couple of things I think we're going to end up slipping in there. For example, one thing is you may have noticed when I listed all those type coercions that you can do in JavaScript, I didn't mention 64-bit numbers because there's not currently an efficient way to represent 64-bit numbers. You have to play games where you chop it apart into two 32-bit halves. And so we'll probably slip in 64-bit numbers into our first version of WASM, and there's a bunch of back and forth debate. One of the reasons that we're targeting the ASM.js level of performance is that there was an idea from fairly early on in the process of this collaboration that we would offer polyfill, and so we'd have an ASM.js module that's able to convert WebAssembly to ASM.js. The exciting thing, to give you a sense of how much sort of forward progress I think we've had in terms of consensus. I've actually heard folks saying lately in collaborating with others, hey, you know, do we really need the polyfill? I mean, we're all implementing this. So it's actually very exciting that I suspect we ultimately will have a polyfill, but just the fact that we're even sort of entertaining thoughts like that is a positive sign in terms of how much agreement there is. Another exciting part of this work is that we're trying to not make some of the same mistakes that were made with both Pinnacle and Emscripten. So one of the, you may be unaware of it, but so both Pinnacle and Emscripten are based off of LLVM, the compiler backend for Clang, and in fact, they're actually based off of the same branch. They have some shared heritage. And unfortunately, one of the things that happened in the early days is that a lot of the functionality that we had hoped that would live in LLVM ended up living in what amounts to a fork. And so there's a very expensive ongoing maintenance burden of merging changes from LLVM into Emscripten and into Pinnacle, and we kind of have shared that work at some points. And this time with WebAssembly, we're trying to do things in a way that's a little friendlier to the LLVM community, and so we're actually developing the backend for WebAssembly upstream in LLVM so that in the long run, what you'll eventually see is that your normal desktop Clang will eventually be able to generate WebAssembly. So the hope is that this will be just a standard part of the kinds of tools that people have on their systems. let's see. So, but what for me is actually the most exciting part of this is actually all of the post-MVP features, the things from native client that I'm excited that we may see soon in the rest of the web. The threads and shared memory, which obviously we're trying to get at this from many different directions. We're also doing the shared array buffer thing, and it's sort of just see which one gets there first. If we have the shared array buffers first, we may expand the polyfills so that we use that as a way to support it. If we get there first with WebAssembly, we'll do that. Same thing with SIMD is almost certainly going to get there first with SIMD.js. So we're, for the moment, avoiding specifying it in WebAssembly, but we'll almost certainly circle back and do that fairly quickly after the MVP. But then we get to the features that NACL has that are kind of unique that I'm hoping we'll be able to get to in the context of WebAssembly. Things like hardware fault interception. This is, you can set regions of memory that you can fault on. This is great if you're trying to implement something like a transpiler or a fast emulator like QEMU, where you want to intercept accesses to know when code regions have changed and that sort of thing. Memory mapping, the idea that you could take a resource and just use the memory system that you have so that you're not making extra copies to get things in and out of the heap of your program. And dynamic linking and shared libraries, we're gonna punt on that for V1 of WebAssembly. And then JIT support, so particularly fine-grained JIT support. So you could JIT a single function, which is critical for, there's some languages like Go and Java where to really get the best kind of performance in this context, you'd want to have JITting support. Just for fun, this is what, so WebAssembly will be a binary format, but we've settled on an S expression-based form for the temporary sort of textual format that we've been using to reach consensus. Part of what we're sort of kicking the can down the road on is what exactly to do about the kind of compression we want to wrap around it. There's a certain irony here that if you've heard the story of the early days of JavaScript, where JavaScript came into being because Lisp was off the table from Mozilla, not Mozilla, sorry, Netscape, not thinking that was a good idea. But now we're back to S expressions and Lispy things, at least in the context of WebAssembly. So planning ahead, how can you plan ahead for that? If you're eager to use this now, your options are NACL and Emscripten, and which you use I think has a little to do on what your needs are. If you need all the features now, NACL is really your only choice. If you want sort of broadest reach, then I would recommend Emscripten, and so there's this sort of a trade-off. It depends on if you need threads, it depends on if you need SIMD, it depends on if you need a number of these things. But the trade-off, of course, is that NACL only works in Google Chrome. In the near future, I think SIMD.js especially will be out of the pipe fairly soon, and shared array buffers will come on soon after, and these will be things that you can sort of add in when they're available. And then somewhere mixed in at the same time and overlap, there'll be the transition to WebAssembly, which hopefully will be an easy transition. All of the tools in all of these different contexts are LLVM-based, and so if you are careful about how you structure your application, it's likely it's just a matter of dropping in a different compiler. So I want to emphasize that this is all happening very fast. To give you an idea of how fast, the SIMD.js standard was only at stage 1 like 6 months ago, and it has raced through. So these things are happening incredibly fast. TC39 has gotten their process down so that they're able to have things happen very, very quickly. So how can you start today on this? I would encourage you to, especially if you're trying to sort of reach everyone still, focus on features you can optionally push to the server. If you can, maybe do the work locally if you have the option of NACL available, and then have low latency, have low latency if it's available, otherwise push to the server. Another option is replace with an alternative experience. So if you have like an interactive physics application, and maybe you substitute in a video on some platforms. Or you can focus on a particular platform. Where this might make sense especially is if you currently are providing an MP API plugin, for example, in the context of a Chrome extension. In a Chrome extension, you have a lot of options. You can even use a conventional native client and have direct access to the instruction set. I don't recommend that in the long term because that's going to be bad for your portability, but if it's as a stepping stone, that could make some sense. I should mention where it runs. So, ASM.js runs in all modern browsers. You at least have to have array buffer. The speed varies, but it's using some idioms that were already things that were being optimized for. So, generally speaking, it runs relatively well. If you're it's lies in benchmarks, so it's how you want to measure it will influence how you perceive the speed. But it's in native territory is the key thing. Pinnacle, you can use it right now. It's live. You can use it in Chrome on any website. So you're free to use Pinnacle, anywhere. There's a number of sites that use it in various contexts. And then you can also use conventional native client, as I mentioned, only in the Chrome Web Store, and you can use any of these, in the Chrome Web Store as well. And also in the Chrome Web Store, there are some additional APIs that you have access to. Like, for example, if you have an application where you want sockets access, you can get that if you're in the Web Store. So go and download an SDK. Many of these are so with the NACL SDK, there's a bunch of examples. If you go down to the examples directory and type make run, it'll compile and run a sample. Emscripten, you can download it. You need to do there's a little install step, and then you can immediately take like a hello world program. They've made it very easy to if you run their MCC compiler, feed in a simple hello world, and then for the output name, if it has .html in the end, it will generate an HTML file, a JavaScript file, and you can go to town immediately. Something I would definitely encourage you to do is leverage the ports that are out there. We've got a collection of applications and libraries that imported a native client called NACL ports. There's 250 something ports. Please use those. Fundamentally, it's a cross compile, so bear that in mind. If you're interested in an interpreted language like Python, Lua, or Ruby, we already have those ports there, so you can take that interpreter and embed that in your application. So this is sort of all it takes to kick off a copy of Python and a Python script and use it in the context of a page. And we've had, for example, that converter I mentioned to convert Android apps uses Python inside of it because we didn't want to have to rewrite our Python script. So you can use Python on the page. So again, I would like to encourage you all to demand the magical things, demand that the web platform does more, and if there are any questions. Yes?
Are we going to get any of this on Android?
So ASM.js will work in some form on Android, and the plan with WebAssembly is that it will be everywhere. So native client does not work on Android for various reasons. Mainly the lack of the context of the Chrome Web Store is the main one, but there's other reasons. Yes?
What are the types of boundaries for performance of memory usage?
Sorry, say again?
What are the boundaries for memory or performance with the native client or the external apps?
So it really depends a little on the app. So Emscripten is going through a lot of the plumbing of the JavaScript engines, and so in some contexts that can work really well. There are a lot of cases where on some browsers, bounds checks and things like that get eliminated or lifted out. There are other contexts where it can work out less well. So it's very application dependent. One of the reasons why I'm reluctant to quote sort of general numbers is that it varies all over the board. Even with native client, it's very architecture dependent. Our 32-bit sandbox is incredibly efficient because we're able to use segment registers to do restriction of data bounds. So there's almost no overhead with that sandbox, whereas some of the other sandboxes have greater overhead. So it's very application and architecture dependent. And it's actually the same thing is true with ASM.js because there's different tricks that you can use in the implementation on different architectures. Yes?
Is there any projects that hold these kind of technologies to outside of the browser, I guess?
So we definitely have some interest in doing this outside the browser. In fact, one of the things we've insisted on with the WebAssembly working group is that there be some thought put in about how this works outside the browser. With native client, there's actually a standalone tool called Cell Loader that lets you load an individual module outside the browser. And there are actually folks that have used this for sandboxing of code server side. It's actually used in various places. At Google, for example, App Engine uses it to sandbox Python in some contexts, and also it's been used to sandbox Go. For example, with Python, there are contexts where your choices are sandbox and native client, and you can skip a more exhaustive security review than if you were outside of NACL, that sort of thing. Yes?
Yeah, so with the minimum viable product version of WebAssembly, what would you expect to be the difference between that and ASM at that point?
So one of the benefits is going to be the encoding size. We're hoping that the minimum viable product will have a more compact encoding, and that will save you time over the wire. The decode is still going to be happening in JavaScript code, so you may have limited benefit in terms of, one of the reasons, by the way, that we want a binary encoding is that it's actually, there's a lot of energy that goes into the parse, and so if we can skip that parse, it would be great. So you'll still have that energy to parse because you're going to convert to ASM, so it's mainly size over the wire. Yes?
Have you ever compared performance with the sheet? You know, we can compile the coding to create.
Oh, you mean with that? You mean just in terms of compared to JavaScript jitting performance?
Yeah.
Oh yeah, I mean the performance is dramatically better because you're able to make these assertions about memory. So the issue is, I mean, all of this in fact relies upon a lot of the same machinery that you're using in your JavaScript engine. In fact, the ASM.js work at both Google and with Firefox builds on the JavaScript engine, builds on the JIT, and so this is just allowing you to do things that you're not able to do in a JIT because in sort of conventional JavaScript, you don't know the types, so you don't know, oh, you know, how many elements are in this this object, you know, what's the memory layout like, and this allows you to say, okay, I know that this is, you know, this many bytes in memory, it's going to stay there, I can iterate over it, and I don't have to do the bounds check, you know, this kind of thing. So it's a huge, huge performance win compared to. Yes, please. Oh yeah, it's here. Let me go back to the beginning here. There you go. It's gonacl.com/magic. GONACL.com/magic. Yes.
Can you just estimate the time frame of how long do we have to finish some version of WebAssembly is actually working in Chromium or whatnot?
So right now we have so we've just the last sort of hurdle we got over with WebAssembly is we decided how we want function pointers to look, at least in the V1, and I believe just the other day we had in our, so for V8 we have a prototype that's landed in a separate repo. We're hoping to bring that over into the main V8 repo soon, but there's a window between when that lands and when it would be, you know, not behind a flag. And so I think landing in the V8 repo is a matter of months. I think deployment without the flag could be months or maybe a year, I think, tops. So. Though I hate to speculate about such things. Standards are a funny business, and it's definitely a lot of debate around the color of the bike shed. Yes? So we continue to plan to support native client for the foreseeable future. There are some interesting things that you can do about it. One of the things I don't know if this talk highlighted sufficiently, but native client has some interesting properties in terms of security that you can't quite assert about things that are generated. One of the advantages of native client is you really only have to trust the security of the validator. And so we have some interesting ideas about where native client might go in terms of leveraging that safety. And I'd like to see some of the stronger safety that we have in native client reintroduced into this space as these standards develop. But it's an ongoing thing. But yeah, we have plans to support native client for the foreseeable future. Thank you.